Okay, it's about 11:05, so we're going to get started with the workshop now. This presentation will be treated as a recap to some of the main topics and issues involved with GIS and mapping data, specifically mapping crime data. It isn't going to provide a huge array of information, but will detail what is necessary in order to understand the following code demonstration tomorrow. Today we'll be discussing what is GIS. We'll then move on to look at the differences between spatial data versus non-spatial data. We'll look at different types of maps, including reference and thematic. We then move on to discuss projection methods and coordinate reference systems and how we basically move from the 3D to the 2D. And we'll also be looking at some spatial relations or analysis, covering autocorrelation, interpolation, and hotspot analysis. I'll then also go on to discuss some data sources for crime and the challenges that come with mapping crime data. In tomorrow's workshop, which will also be held at 11 a.m., we'll be discussing or working through kind of four main topics. And this involves first looking at descriptive analysis of crime data. We then move on to discussing shapefiles and how to attach this to our crime data. We then move on to combining our census data to this data to allow us to establish crime rates. And then lastly, we'll look at those spatial relations and analyses, specifically hotspot analysis and interpolation. There's also some extra topics, including how to make interactive maps via leaflet. And depending on time in tomorrow's workshop, we'll see if we can get through those. The material for the live code demonstration can be found in our GitHub stored here. And I believe Emma has popped that in the webinar chat. Don't worry too much about exploring that just now, because I'm going to explain to you how to obtain the data and the code at the end of the workshop, where we'll stop the live share and I'll basically demonstrate how you can clone the code onto your computer or how you can access the interactive notebooks. So let's get started with our topic. So what exactly is GIS? GIS stands for Graphical Information Systems. These are pretty much a theoretical framework that allows for the creation and analysis of spatial and geographical data. It can be viewed as quite an abstract platform that integrates data onto a map using various methods. We see GIS present in almost every field and every organization, It's not only a way to share information, but also a way to solve complex problems around the world. I'd say that the biggest benefit from GIS is for us to explore trends and patterns to be studied visually, which basically provides a new form of analysis. Just a little quick history lesson about GIS. It was established by Roger Tomlinson, Dr. Roger Tomlinson, in the 1960s, and he was commissioned by the Canadian government to create a usable and efficient inventory of their natural resources. He had originally tried various manual methods for overlaying these environmental, cultural, economic, and political variables, but he found that all were too timely or too costly. So he basically helped to create this automated computing system, and he was then known and still is known as the father of GIS. From here, we've obviously had a lot of advancement and a lot of development, such as the ESRI, which is the Environmental Systems Research Institute. This was established by Laura and Jack Dangamond, and they basically developed more advanced softwares for mapping and spatial analytics. It's important to note that many datasets you will encounter in your lifetime can all be assigned a spatial location, whether this is on the Earth's surface or whether it's some arbitrary coordinate system. So the question that you need to ask yourself is, does it need to be analysed by a GIS environment? So let's look at these two examples here. In option A, you are interested in identifying the 10 cities with the highest average income scores. In option A, you would simply need a table that looks like this. You've got your two variables. You've got your city and your score. And this allows you to identify the highest average incomes in those cities. However, if you're interested in option B, where you want to identify whether these 10 cities are geographically clustered, you're going to need a bit more information specifically about the shape of the country and its geographical location. This is where you'll have a table that maybe looks something like this. So in this instance, we've got three variables, which includes the city, the highest income, and the spatial boundaries. This will then allow us to basically map these countries with the highest incomes and show how these are geographically clustered. All data in GIS are georeferenced. This means it either has an attribute and a location. So geographic informations contain an explicit geographic reference such as latitude and longitude, or things like national grid coordinates, and implicit reference such as, addresses, postcodes, census tracts, or even road names. So we use an automated process called geocoding to basically create these references from implicit references. So these geographic references allow you to locate features such as businesses or forest stands, or even events such as earthquakes on the Earth's surface for analysis. For crime data, an attribute might include who/where the call was received, or simply just the type of crime that was recorded. There are various softwares available to run GIS. The main ones are listed on the screen. We have Geoda, ArcGIS, FME, QGIS, and R. There are pros and cons to using each and one of these systems. Obviously, in this workshop, we're going to be working with R and its IDE RStudio. I think it's a great platform for allowing for not only spatial data analysis, geovisualization, spatial autocorrelation, and things like spatial modeling as well. And because there is such a large amount of packages that have become available, it makes it very, very easy to run this spatial analysis in our studios. Just out of curiosity, I was wondering what softwares do you use, or what softwares have you stumbled across, just so I've got a bit of a better idea about how to run the code demonstration tomorrow. So if you want to head back over to Mentimeter and fill out the poll, I'll just give this a couple minutes. Okay, that's great. It looks like the majority of people in this workshop do tend to use R for their spatial analysis or spatial mapping, which is great. Not followed quite closely by Excel. And we have a few users who have used Python and Starter as well. This is good to know where everyone kind of stands. This is kind of just for this is just me being nosy to figure out what the most popular system is. So great, thanks for filling that out. So let's go on to discuss how is GIS used. There are multiple ways that GIS can be used. For example, to identify problems, monitor change, manage and respond to events. You can even perform forecasting. So this is to make predictions about what we expect to see in the future. We can use it to set priorities, and obviously this is done quite heavily in the policing world. And of course, most commonly is to simply understand trends. Maybe you're interested in exploring why burglary rates have increased in 2019 but decreased in 2020, something like that. Here are some questions that GIS allows us to explore specifically with crime data. So one question that a lot of people do explore is, where are the most vulnerable communities located? If individuals want to use crime maps to, for example, safeguard, their personal safety, then avoiding areas with high level of street robberies would be, this is how someone would use that to basically target that. So then clearly a geographical representation of the crime would be appropriate to understand where the most vulnerable communities are located. Another question that you might be asking to kind of explore crime data would be, why do crimes occur in one area and not the other? If you come from a criminological or sociological background, there are several theories that help to explain why crimes occur in some places and not others. such as the crime pattern theory. This theory basically integrates crime within a geographic context, then demonstrates how the environment that people live in and pass through influence the criminality. So this theory specifically focuses on places and that lack of social control or other measures of guardianship that kind of are needed to control crime. So, for example, in a suburban neighborhood, this could become a hotspot for burglaries because some homes have inadequate protection and there's nobody home to guard this property. Maybe you're interested in how offenders travel to the crime location. In other words, what is it about one specific place that convinces an offender to commit a crime here over an alternative location? And there are a few reasons that affect how a offender travels. The first is being the offence type. So there was a bit of interesting research done by Ackerman, I believe, in 2015, and he found that in general, violent crimes had a shorter median distance than property crimes. This was 4.2 miles compared to 5.7 miles. Another reason could be the age of the offender. In general, adolescent offenders are to travel shorter distances compared to older offenders simply because they have less means of travel. There's also some interesting studies surrounding gender, but this has kind of been a bit more contradictory in that some research has shown that females travel further than male offenders for property crimes, while others have shown the opposite. So there isn't actually a clear trend when it comes to gender, but when we look at age, there is much more consistent findings. And then you can start to look at other things like neighborhood affluence and target suitability to kind of understand how offenders travel to the crime of a location. And just the last question that is quite a common question when exploring crime data is, where are there more or less stop and searches than we would expect in relation to the distribution of crime? So by this, I mean, by comparing the actual distribution of the crime and the level of stop and search, we can then start to question the necessity of stop and search. Can we use this as a tool of crime reduction or a tool for crime detection? And this is when you can start to question police powers and the kind of sociological concepts to stop and search. So moving on from this kind of theoretical abstract understanding of crime data, I'm going to draw on to now the differences between reference and thematic maps. So GIS are known to produce two very broad types of maps, and these are known as reference and thematic. Reference maps are used to communicate location on more static data points. So we simply use this to pinpoint data on a map, i.e. we're just referencing what we see in our physical environment. And this is where we might witness a very descriptive map. On the other scale, we have something called thematic maps, and these are used to highlight a spatial relationship, i.e. to study a theme within a map. And this is where we start to become much more explanatory. This is where we're looking for things that we can't see with our eyes. We're looking at themes are hidden within the environment. So here's just a little image to show you the differences between the two. On the map on the left, we have a reference map. And this is a very common map that we've probably all seen. And it's simply just a map that highlights natural patterns and synthetic features. If we were to zoom into this map, we would start to see, the positioning and the heights of the mountains, or we might even see the layouts of bus routes and like motorways. So this type of map is simply referencing what we see in our physical environment. When we compare this to the map on the right, which is the thematic map, what we're seeing here is a map that is highlighting a spatial relationship. This thematic map is basically how we map a particular theme to a geographic area. So this is where it starts to help us tell a story about a place. And it's commonly used to map subjects such as climate issues, population densities, health issues, demographics, and of course, crime itself. So sometimes the difference between the reference and thematic maps can become confusing. So let's take at a example that was done called Lives on the Line. In this study, they found that most government statistics typically are mapped according to what we call official geographical units, such as wards or lower layer super output areas. And you might be thinking, what does that mean? What are you on about? Well, that's exactly the point. What they wanted to do was move away from using these geographical units and start to look at um, areas that are kind of more common that people would understand better. So this is where they tried a new method back in July to basically show life expectancy statistics in a fresh light by mapping them on the London tube stations. So this provides us with a really detailed story about life expectancy statistics and the differences across London using tube maps as the main geographical unit. So you might be thinking, well, is this a reference map or is this a thematic map? You might think they're thematic because, of course, they are mapping a particular theme to this geographic area, right? They're mapping that like life expectancy, that story to a geographic area. And yes, you would be right. This is indeed a thematic map. But at the same time, it does also provide a reference map because what we're seeing here is the tube maps simply pinpointed, telling us where the tube maps are. So in a way, this Lives on the Line study is kind of conveying properties of both a thematic and a reference map. If you'd like to head back over to Mentimeter, we're going to participate in a little quiz where we explore a few scenarios that help us to understand the differences between the two. So, in scenario 1, let's just say that you are visualizing road networks to improve road safety measures. Would you class this as a reference map or a thematic map? And if you're unsure, that's absolutely fine as well. Please go ahead and put that in. No answer is wrong. So I'll give you a couple minutes just to think about this. That's great. We've got 2 people who have said unsure, and we've got the rest have said that this is a reference map. So let's break this down a little bit. At first glance, this might be said to be a type of reference map. I would agree, because what we are doing is simply pinpointing existing road networks onto a map, right? It's giving us what we see in the physical environment onto a map. However, you might argue that this could also be seen as a thematic map because we are studying the existing road networks to then improve road safety measures, which arguably is a type of accident analysis. So, for example, there might have been the introduction of speed signs or zebra crossings outside schools or residential areas due to reports of accidents/dangerous driving. So, we are studying spatially the relationship between the road networks and the accidents, and we're mapping this particular theme to a geographic area. So, if you have voted reference maps, you are indeed correct. But yes, if you look a little bit further, you can start to see why this might also play as a thematic map, as we're using it to improve road safety measures. All right, I'm going to move on to scenario 2. The visualization of the Earth's surface showing its elevation is a type of what? Would you class this as a reference or a thematic map? Again, if you're unsure, please feel free to include that. The votes are still coming in, so I'm just going to give that 30 seconds or so, and then we'll discuss the correct answer. Okay, so the majority of users have said that this is indeed a reference map, with a few people voting thematic and a few people voting unsure. So let's go ahead and discuss what the correct answer would be. I would argue that the visualization of the Earth's surface showing its elevation is indeed a type of reference map. This is what we would call a topographic map, and this refers to basically a graphical representation of the 3-dimensional configuration of the surface of the Earth. So in short, it's basically describing where the Earth's surface is elevated. And if you've ever gone on walks or done anything like DOV, you'll know that these maps are normally represented by what we call contour lines. And these contour lines show you how basically elevated an area of the Earth is. So yeah, I would argue that this is simply a reference map. Again, depending on your kind of research questions and your intentions, you might also argue that this is a type of thematic map. And this is because research has suggested that studying a topographic map is a great way to learn how to match terrain features with the contour lines on a map, such as the steepness of the terrain, the weather, whether this is above or below sea level. And so in this instance, you might interpret that what we are studying spatially is the relationship between contour lines to the different features of the Earth. So if you answered any of the options, I would consider yourself to be correct. Either way, this kind of answer is open to debate. And this is the difference between mapping places and mapping data. I believe we have just one more scenario here for you. Navigation tools such as Google Maps or Citymapper, can they be classed as reference or thematic maps? I'm not trying to trick anyone out, so please go ahead and vote what you think the answer would be for this. It looks like the majority of people are saying that this is a reference map, and we have a split between this being thematic or unsure, and that's absolutely okay. We'll just wait for a couple more votes to come through. Maybe I'll give this 15 seconds or so, and then we can have a little discussion about where navigation tools fit in the concept of reference and thematic maps. So yeah, immediately you might assume that this is an obvious type of reference map, which is what the majority of users have voted for this question. It highlights the important physical features needed for travel, such as bus routes, walking routes, and cycle lanes, for example. However, yes, reference maps portray, the basic sets of features, such as transport routes, but can we say that an app that plans your travel is a type of reference map? Because what it does do is uses AI algorithms to basically get you from one place to another, normally choosing you the fastest or the cheapest route, right? So can we call this a thematic map instead, since it's overlaying information onto our base map? And this brings us on to a really important topic when understanding GIS and spatial data. And this is the distinction between analog and digital maps. This takes us back to Roger Tomlinson, the father of GIS, and his automated computing system. And it kind of draws importance to analog versus digital maps and their place that they have in GIS. Researchers recently have considered navigational tools to be fundamentally different from both reference and thematic maps, which kind of opens debate for this third category, right? But it could be argued that, all maps are navigational depending on how you use them. The difference is that a digital map, one that is specifically interactive, like Google Maps or Citymapper or even Waze, um, is that obviously these are specifically interactive. And this kind of links us back to what Roger Tomlinson said. He couldn't overlay his data onto an analog map, so he moved towards computation. So one way I like to see this is that the main difference between reference and thematic maps is that thematic maps are far more interactive, which is why navigational tools might be considered to be a type of thematic map. So just to sum up, although maps fall broadly into these two categories, there are ways in which these types of map overlap or share similarities. And the way I like to kind of understand this is that every thematic map is a reference map in that it includes kind of that underlying base layer physical information about the physical environment, but not every reference map is a thematic map. And this decision is up to you. It's not entirely necessary to define these in your work, but I do think it's important to know what type of map you want to make, as these can be affected by the type of data that you have. So just to give you guys a chance to think a bit more in depth, can you give any examples of types of maps that might share qualities of both thematic and reference maps? So think about any maps that you have worked with yourself or have read upon or studied. And can you think about any of these maps that share the similarities between both thematic and reference? So any maps that are both highlighting physical features as well as telling a story, you know, about this area. I will give this section a minute or so and we'll see what responses we get. This is great. We've got a lot of examples coming through at the moment. Yep, weather maps are a great example along with flood data maps. What we're seeing at first is a map of a area, it tells us whether this is broken down by, I don't know, ward or census tract or postcodes. And then we see this overlaid information, right, about the weather and about the floods. And that's simply adding a story to a like static map. Population density maps, that's a great example of a thematic map, as well as obviously having the properties of a reference map. Hotel maps and restaurant maps, that's a great example as well. What we tend to see is the, physical environment of restaurants and then overlaid this onto our like base maps, hiking maps, housing price gradient maps, that's a great example. Historical maps with contextual information, that's a great example too, because that's exactly what Roger Tomlinson kind of established to do when he was looking at his Canadian resources. And as you can see, Mentimeter has nicely grouped these into kind of some broad categories that you guys have established. I see there's still new responses coming through, so I'm going to just give us a minute. Service area maps, 20-minute neighborhoods. Yeah, that's a great example. COVID-19 cases, numbers on a map, another great example. Hiking maps, great example as well. Of course, this is where we like draw it back to looking at the contour lines on our maps. I believe that if the lines are, I might get this wrong. I think if the lines are closer together, then this shows that the Earth is more elevated in that area. And if the lines are further apart, then the Earth is less elevated. I might have got that mixed up, but yes, that kind of general principle. Traffic flow, that's a great example of a map that shares both thematic and reference map qualities. I don't think I've ever had so many votes in this question, so thank you all for participating in that. Just other examples that I don't think I've been included in here would be time zone maps as well. We would also have things like flow maps. I guess, yes, the traffic flow is an example of a flow map. We'd have heat maps. This is mainly used when we're looking at crime data. We've got chloropath maps, cartograms, or even datametric maps as well. So these are all types of kind of thematical maps. Great. Now we've had a pretty in-depth understanding of what these two types of maps are from our GIS systems. We're going to move on now to looking at the differences in spatial data. So what is it? What is spatial data? Spatial data, in short, is simply a representation of the real world. It attempts to represent all the physical features of the data in an accurate way. And typically spatial data, also known as geospatial data, just in case you hear me interchanging between the two, it's just a data frame that contains information about a specific location, which can then be analysed to better understand that location. And GIS enables this spatial data to be processed and analysed. Unfortunately, we can't always use systems like Excel, because some systems like Excel don't have the correct packages to basically deal with the spatial boundaries that exist in the spatial data. And this is where the GIS enables us to basically better process and analyze these. So there are two types of spatial data, vector and raster data. Our key focus is going to be on vector data. and I'll briefly just describe to you what the difference between the two are. Vector data is the most common format, and this is typically the one you'll be working with in our crime workshop tomorrow. And vector data consists of points, lines, and what we call polygons. Point data is simply a pair of coordinates. So in the context of crime, this might be the location of a burglary report, for example. So this is exactly where that burglary was reported. It's given a latitude and a longitude, and it pinpoints exactly where that had happened. We then have lines, and these extend the points, and they include at least 2 points. So this could be, for example, the street that that burglary call was received on. So it kind of like zooms out in a way. So imagine you're looking at a map, and you're looking at one specific area, one specific point, and you zoom out a little bit, and then you get that street name. That would be the lines. You then zoom out a little bit further, and we get what we call the polygons. And the polygons would typically represent the area, the city, or the ward that that street belongs in. And a polygon has a connected boundary. So, you know, think about your local Tesco Express, for example. That would be the point data. If you zoom out a little bit, you'll then get the street name that that Tesco Express lives on. And you zoom out a little bit more, then you get that city where that Tesco Express lives within. And these are the three types of data uh, points that are obtained in a vector data. Raster data, I won't talk too much about it. It's simply just imagery or satellite data that are formed from a grid of pixels. And yeah, unfortunately, you can't manipulate the information from raster data. You can't like move a place name around, or when you zoom into the map, it then also becomes more pixelated and unreadable. So these raster data is typically suited for representing data that changes continuously across a landscape or a surface. Um, it's just a method for storing the like continuity of surface. So things like temperature, for example, would be recorded using raster data, where each pixel represents a different value or attribute within the overall range of values for the data. But yeah, it typically works with data that is continuously changing, like temperature. So there are two primary data types, as I mentioned, the raster data and the vector data. Raster data would use typically files named geotiff files, and we're going to pretty much brush over that because we don't need to know too much about that. But for vector data, typically the most common format are what we call shape files. And here is a file extension of a shape file. And what we see is uh, basically a folder that contains multiple files that work together. The s.shp file stores the geometry. The s.dbf file contains the attribute data. So this might be, for example, the crime type. And then you have the .prj, which is the projection systems, and the coordinate systems, which we're going to talk about in a minute. But I just wanted to show you guys what a shapefile might look like. And it's just a multiple file that contains multiple information about a specific like spatial data frame. So if this was a crime data set, for example, you'd have information about the crime type, you'd have information about the street this was on, you'd have the information about the longitude and latitude, and then you'd also have the kind of like the border of whichever areas that you're looking into. So when managing these GIS files in R, remember this is a vector data, um, there are normally two key packages that you would use, and this would be a simple features, which is the SF package, and the RGDL package. The simple features package is a modern package for handling spatial data. And this code snippet here demonstrates a very simple but kind of concise way about how you might read in a shape file. So you start by reading in a shapefile, and then you have to then transform the coordinate reference systems, which we're going to talk about in a minute. And there's just some basic code to show you how to then plot a shapefile. But yeah, I just wanted to kind of demonstrate a little example about what a GS file might look like in R. So yes, while vector data excels in representing the geometry of spatial features, it does introduce us to a complex interplay between spatial accuracy and spatial analysis. And this interplay is where we encounter the modifiable areal unit problem. And this is a fundamental challenge in spatial analysis that affects our interpretation of spatial data. So let's talk a little bit about what this problem is. So this simply refers to the cartographic representation of data whose attributes are significantly influenced by the spatial scale used. So in short and in more layman's terms, it's basically saying that same basic data can yield different results when aggregated differently. This applies to where data are aggregated to areal units. So, if you aggregated data to, let's say, to postcodes compared to wards, you might receive, a much different interpretation about this kind of crime trends in those areas. There are two aspects to understanding the MAUP, and this is the scaling effect and the zoning effect. The zoning effect is also known as the aggregation effect, just in case you have heard those phrases. But yeah, the scale effect is simply changing the size of the spatial units, so from neighborhoods to districts, can then alter your statistical results, such as the means or the totals, right? And the zoning effect, or the aggregation effect, alters the shape or the configuration of spatial units, even if the scale remains constant. And this can also impact your results. For example, grouping neighborhoods into districts in various ways can reveal, or the opposite, hide different spatial patterns or phenomenon, like, I don't know, poverty or disease, or again, crime. So here's a little image to kind of just show you the visualizations of like a scale effect and a zoning effect. So the image at the top is the scale effect, and an example of this would be like aggregating crime at city level versus neighborhood level might give different insights. A high crime district might disappear when aggregated to a larger region, like we see here. In that map on the left, we're using smaller spatial units compared to the map on the right. And if you was to present these results to an audience, you really need to think about the interpretation of that data, right? Because it changes what we as the audience would see as which areas have the highest level of crime. And this also brings us to the question about, what what kind of aggregation should police be using, It would obviously make sense to use much smaller units for the police because then they have better ways to introduce policies to areas that are affected by these kind of high crime districts compared to areas with bigger aggregations due to the increase in variability. In this spotted image where we have the zone effect, this is again, so the way we draw boundaries affects results. For example, changing police district boundaries may change, for example, your crime hotspot rankings. So crime rates might appear lower or higher depending on how these zones are drawn. Yeah, I hope that was clear enough in understanding. And just to make sure it is, have a little quiz for you guys about the MAUP. So true or false, the scale effect in the MAUP refers to changes in statistical results caused by the size of the geographical unit used in the analysis. Is this true or false? I'll give a minute or two just for those answers to flow through. That's great. I think everyone's caught on that the answer is in fact true. And yeah, so this is true in that, yeah, using finer analysis will inevitably lead to different analysis results, right? And this is because the scale effect causes variation in the statistical results between different levels of aggregation. Another little quiz for you guys. Which of the following best describes aggregation effect in the MAUP? Remember, this aggregation effect is also known as the zone effect. Does it refer to the impact of data collection methods on analysis outcomes? Or is or does it describe how the arrangements and shapes of spatial units can alter statistical results? C, is it the effect of atmospheric conditions? Or D, it denotes the influence of unit size on data storage requirements. That's great. Majority of people are voting that this is indeed option B, where it describes how the arrangement and shapes of spatial units can alter statistical results. And if you have voted B, you would in fact be correct. The aggregation effect is observed when the scale of analysis is fixed, but the shape of the aggregation units changes. So, for example, let me try give an example. If you use data aggregated to 1 mile grid scales, this will obviously be very different to using data aggregated to 1 mile hexagon scales. And this zone effect, is a problem because it is an analysis, at least in part, of the aggregation scheme rather than the data itself. So I'm basically just trying to show you guys that, yeah, depending on how we use and aggregate this data ourselves, there will be huge implications for how users then interpret your results and your analysis. So before we move on to a little break, I have one more question for you. Just to get you guys thinking about what are some potential implications of ignoring the modifiable areal problem in crime spatial analysis. So what if we were just to basically ignore the scale effect and ignore the zone effect? What problems might occur when mapping crime data? I'll give this a minute or so, see if any answers come through, and then we'll go ahead and take a quick 5-minute break while we move on to the last final topics of this talk. Feel free to just include one word. I'm not asking for any sentences or anything. Yep, resulting in inaccurate statistics, absolutely. Again, this is where we really need to think about the differences between comparing data at different aggregated levels. Make high crime areas, mask high crime areas due to just the scale chosen. Exactly that. I'm glad we're all kind of understanding the importance of this modifiable areal unit problem. We then have the creation of false hotspots for sure. If we tend to use a area of a larger scale, we're going to basically reduce that variability within our data set and kind of misleading, where these hotspots actually do occur. Perfect. Countermeasures are not targeted. You might overlook some hotspots in the middle of a low crime area. Exactly. You might give the statistics at the level you cannot intervene afterwards. Absolutely. These are great answers. Correlation versus causation. Perfect. This is exactly what I wanted to hear. I'm glad everyone has understood the importance of understanding why the level of scale you choose is so, so vital for your implications as a researcher, so vital for it's almost like as the researcher you are dictating what your audience will inevitably read and see, and typically if you're not coming from a background where you understand all of this like geographical units, you will take what you see as face value, right? And this is why we are fed so much false information about certain crime types and areas, because people kind of fail to think about the effects of these scale and aggregation effects within their data. Another interesting point that I just wanted to raise here is that once all of this happens, once we look beyond the statistics, what happens to policy? What happens to resource allocation, Law enforcement agencies rely on these spatial analysis of crime to basically allocate resources efficiently. And if this MAUP is not considered, there is a high risk of misallocating these resources to areas that arguably might not need it and neglecting areas that do need it. So there's a huge impact on policy development and evaluation when we start to think about the MAUP. There's also this, idea of like public perception and community relations and how they can be significantly influenced by how this crime is presented. Um, of course, there's things like the ethical considerations as well, when the implications of, ignoring this MAUP can lead to policies or actions that disproportionately affect certain communities. And it's essential to basically consider this fairness and justice of crime prevention strategies that are based on potentially biased spatial analysis. Um, so yeah, recognizing the implications of the MAUP presents an opportunity for innovation in crime spatial methods, developing and applying new analytical techniques that account for this problem can improve the accuracy of not only crime pattern analysis, but also inevitably lead to more effective crime prevention strategies. All right. I don't see any questions that have been added into the chat or the Q&A. If you do have any questions, please feel free to leave them there and I will answer them at the end of the workshop. But yeah, we're going to get a move on because I realise there is a few more topics that I want to discuss with you. So yeah, this brings us on to our projection methods. So we have this basic understanding of spatial data, and this is where we can ask, how do we actually pinpoint a location to a map? How do we basically move from the 3D to the 2D? How do we transform the Earth from its spherical 3D shape to a planar 2D shape? And I always like to use the example of this football. So imagine you have a football and you begin cutting up with a knife. Now, it wouldn't fit together perfectly if you had tried to recreate this into a rectangle or a square or a triangle per se. So these projection systems are simply equations that tell a mapping system how to populate a new shape or area. So if we wanted to create a rectangle, for example, it might look something like this, where the whole area is populated. Now, it's important to know that during this process, we can basically have something called distortion. And these projection methods tend to basically distort or misrepresent not only the area, the shape, the distance, but also the direction of points. Now, typically, there are algorithms in place to kind of control for this misrepresentation, but not all of these are preserved. So, imagine you had a map projection of, imagine you had a map projection as an attempt to reconstruct your face into 2 dimensions. Some maps will get the shapes of all your features just right, but not the sizes. Others will get the sizes just right, but not the shapes, And this is the same way, this is the same thing basically that happens to maps. And it depends on which, attributes you're willing to compromise. A lot of mapping systems tend to compromise the distance, others tend to compromise the shapes, others tend to compromise the area. Typically, there's a sweet spot in between, and these mapping algorithms tend to do this for you, but it's always important to know that there can be misrepresentation of one of 4 areas. There are 3 distortion families. I'm not going to talk too much about this. Within each of these families, there are hundreds to thousands of different types of projections. They are not really necessary to know here or today. But here is a quick example of how a map that we are all familiar with, is distorted because of using different projection methods. So let's have a look at this example here. In this slide, we have 2 maps. We have one made by the Webb-Mercator projection and one made by the Gao-Peters projection. The map on the left is one you're probably all familiar with, and this is widely used. This is what Google Maps and OpenStreetMaps and Waze and kind of every software that we see um, is uses the web Mercator projection. And this tends to preserve angles and shapes, which is useful for navigation. However, it distorts areas, making regions like the North Pole, near like Canada and Russia and sorry, not the North Pole, near the poles, like the Canada, Russia, Greenland, and they basically appear much larger than they actually are. Now, this is relevant to crime mapping because if you're mapping crime across a large area, using the web Mercator may represent the relative size of high crime areas. So these crime densities in smaller equatorial regions might look less significant compared to like larger, exaggerated polar areas. Now, if we compare this to the map on the right, which is the Gauss-Peter projection, this map preserves area but distorts the shape. So it ensures that all countries and regions are shown at their true relative size. Again, if we look at the relevance to crime mapping in this, if you're analysing crime per capita across these different regions, this projection is more appropriate because it actually represents the actual land area, right? Because it's keeping the area size but distorts the shape. So crime statistics by region can appear more balanced, avoiding this kind of false impression that larger looking regions in the web Mercator have more crime just because they appear bigger. So yeah, that's just a quick example about distortion and the effect that that the projection system can have. So we've talked about moving from the 3D to the 2D, right? But how do we actually do that? What systems are in place in the GIS world that allows us to move from the 3D to the 2D? This is where we come to our coordinate reference systems. Every place on Earth is specified by three main numbers. That's a latitude, a longitude, and an altitude. And each number indicates the distance between some point and your fixed reference, also known as your origin. There are two main coordinate reference systems to be aware of, and these are known as the geographic coordinate system and the projected coordinate system. The geographic coordinate system on the left is the where. This defines a location on the Earth's surface using latitude and longitude. So, for example, crime incidents are recorded with GPS coordinates using what we call the EPSG, which we'll be looking at tomorrow. And then the projection on the right is the projected coordinate system. And this is how we translate the 3D globe into a 2D map, kind of optimizing for area, distance, and direction. So for example, a crime heat map for a city may use a local projection, like a British National Grid, for example, for better accuracy. So yeah, that's just a quick information about the coordinate reference systems. These become much easier to understand, especially when you start to work with the data yourself. So tomorrow we'll be looking at basically how to transform a data set using the correct coordinate reference system. But yeah, if you're just interested in how this might look, it's important to ensure that the data is stored. Sorry, when working with multiple forms of spatial data, like we will be doing tomorrow, it's important to ensure that all data is basically stored in that same coordinate reference systems, or they will fail to line up with the graphical information system. So tomorrow we're working with the census data, the crime data, and the shapefile. We have to ensure that each of these data frames are within the correct coordinate systems or our projections will not work. The decision on which system to use kind of depends on the regional extent of the area you want to work in, or the analysis that you want to do, and often the availability of the data. So key takeaways from this is that the GCS, which we see at the bottom here, this tells me where on Earth the data should draw. And the PCS tells me how to draw the Earth on a flat surface. So yeah, for example, if we're analysing like burglary hotspots, for example, then an appropriate coordinate reference system ensures accurate distances and spatial relationships. Fab. All right, we're going to move on to looking at our spatial relations and analysis in GIS. So spatial relations refer to the ways in which different locations, areas, or objects are situated in relation to each other on the Earth's surface. So this brings us back to our reference maps, right? And then we have our spatial analysis, and this refers to studying entities by examining, accessing, modeling, evaluating all those spatial data features. And this kind of brings us back to our thematic maps. We know that crime doesn't occur randomly, and this is why the importance of spatial relations in crime analysis is so important. You know, they have patterns that are influenced by not only geographic, but also environmental factors. So we use these spatial statistics will allow us to quantify these patterns and make data-driven decisions in crime prevention and resource allocation. So let's take a look at the three most common spatial analysis methods you might see when working with crime data. But before doing that, I just wanted to know what spatial analysis you might have worked with or read upon in your own work, and then I'll go ahead and describe the three that we'll be looking at tomorrow. So feel free to enter this into the poll. Choropleth maps, that's a great example and one that we'll also be looking at tomorrow. These are great to basically show how data changes from place to place. It allows you to basically visualize this information tied to geography and then to compare this across data from different locations. Network analysis, that's a great example. I've not necessarily worked with network analysis in GIS myself, but what I'm familiar with is that it examines the properties of geographic networks, right? Like roads or pipelines, to then understand the flows and the accessibility used using tools like I think it's the shortest path analysis and service area analysis. That kind of network analysis is a great one for understanding transportation or even understanding the movement of vehicle crime, for example. That would be really interesting. Got geographic weighted regression. I believe that just takes non-stationary variables like demographic, right, and climate, and then models the local relationships between these predictors and an outcome of interest. Yeah, something like that. Great, there's loads of examples here. Earthquake maps, yeah, that's a good example. Hypothesis testing, great example again. We then have small area estimation analysis. Yeah, this is a great example and one that we're vaguely going to touch on tomorrow. But SAE is a technique basically used to create reliable estimates for smaller geographical areas or subpopulations where the data is insufficient. So by combining survey data with this whatever data source you're using, you're then interpolating missing data into the data. And this brings us on to one of our topics that we'll be looking at tomorrow, which is spatial interpolation. So we're going to be looking at how to address areas that have missing data and basically how to establish an aggregated statistic for that area with the missing data. So let's just go on ahead and discuss some of the main analyses you might stumble across when using or when exploring crime data. And this simply brings us on to a point pattern analysis. This is probably the most fundamental and the most basic spatial analysis technique used to study crime distribution. You know, crime incidences are often recorded as point locations, as we've mentioned. So this will be to longitude, to latitude. And this PPA, the point pattern analysis, helps identify spatial patterns within crime data, whether crimes are clustered, disappeared, or randomly distributed. There are many methods of point pattern analysis, and this includes basically just making simple point maps. And the left map shows individual crime rates, for example. And typically, when when using point pattern analysis, one of the main limitations is that the maps can become very overwhelming very quickly due to like the large amount of data, especially when working with crime data, and especially working with crime data from multiple years. So this overplotting can make it difficult to see meaningful patterns, but this is where we apply things like kernel density estimation, and this converts points data into a heat map by, estimating the intensity of crimes in that area. Or you can use nearest neighbor analysis, which I think was mentioned in the previous method. I've just seen a question that asks, does it include any statistical testings? Yes, just yeah, like kernel density estimation is a statistical testing for point pattern analysis. You can also use things like grid-based aggregation, which what's the other name for that? Hex binning. That's it, hex binning. And this is basically where you aggregate into like hexagonal bins, making the patterns more interpretable. Um, yeah, then you've got nearest neighborhood analysis, where you measure how close crime events are to each other. And, you know, for example, if burglaries are happening within a small radius, then the police can focus patrols in that area, right? So this point pattern analysis and hotspot analysis kind of interfere with each other, but uh, it does depend on those statistical testings that you imply. So why is it important to use PPA? The most obvious answer is that it helps detect crime hotspots and allocate police resources efficiently. It can, reveal patterns that are not visible in a normal raw data set, and it does support predictive policing. Another analysis that we'll be looking at tomorrow is spatial autocorrelation, and this is a technique that measures the degree to which crimes occur near each other in space. So it kind of helps us understand how crime rates in one area relate to crime rates in those nearby areas. Um, so what does this map show here? Well, this map divides England into hexagonal bins, each representing an area with calculated crime rate. And these areas are coloured in shades of a single colour to show different levels of crime. Typically, darker areas indicate regions with high crime rates, and then the lighter areas indicate low crime regions. So this visualization highlights crime clusters. And again, there are a few key statistical methods used in this process. The main one being the Moran's eye, which measures whether crime is clustered, what we would call a positive autocorrelation, or whether crime is randomly distributed. So this really does help us to understand the relationship between crime in neighboring areas. Another key statistical method is the local indicators of spatial association, also known as LISA maps, and these identify specific hotspots and cold spots of crime. So why does this matter for crime analysis? Well, again, this is quite simple because it helps police allocate resources effectively. If crime is highly clustered, then interventions can be targeted in specific areas. It also helps to detect what we call the spillover effect. So, for example, if a police tackle crime in one neighborhood, does this crime move to another neighborhood area? Just because we're reducing crime in one area, this kind of spillover effect questions whether does crime just simply move rather than does crime reduce? Um, yeah, so that's that. And tomorrow we'll mainly be focusing on our spatial interpolation as one of our main analysis, which I think is a really, really useful technique to use, especially when starting out understanding crime mapping. And it uses a gradient of colours to interpolate crime rates between known data points, creating a smooth transition that again estimates the crime rates in the area with no direct data. So in layman's terms, basically saying if we've got areas that have missing data, then we can use spatial interpolation as a way to obtain all the averages from neighboring areas to establish an area establish an average for that area that is missing. Um, it does this by using what we call inverse distance weighting, or the IDW, and it basically says um, nearby crime points have more influence than distant ones. Yeah, sorry, so near crime points have more influence than the distant ones. There's also things like the Kriging method, and this is just a method that considers spatial autocorrelation to provide better crime rate predictions. So again, why is this important for crime analysis? Well, this helps to basically fill gaps in the crime data, you know. It helps estimate crimes in areas without police reports. Obviously, it does make us question the efficiency of using um, estimated crime counts. You know, how effective would that be to resource allocation? It might be better for simply understanding the trends, but could we actually use this as a tool for police prevention? Questionable. Um, and the last one that we have briefly spoken about is, of course, our hotspot analysis. So this map highlights areas with significantly higher crime rates in bright colours um, against a neutral background, indicating geographic concentrations of high crime rates and identifying areas needing immediate attention. Now, I won't speak too much about this because, again, this uses what we know as the kernel density estimation, or again, the local Moran's eye. Sorry again. But yeah, this is really important in crime mapping again because it helps us focus on those resources on helps us with police resource allocation on those high crime zones. Um, it allows authorities to design better public spaces to reduce crime risks. It's that simple. So tomorrow we will be looking at hotspot analysis, we'll be looking at spatial interpolation, and we'll be looking at point pattern analysis. Um, there's a question in the group chat, sorry, the webinar chat that says, will you cover Krigings tomorrow? Let me just have a think. We don't go into too much detail about Kriging tomorrow, but I simply introduce the packages that are needed to run the statistical Kriging test. And that will be done towards the fourth topic in the code demonstration tomorrow. We're coming towards the end, so I just wanted to draw your attention on some of the data sources for crime that are out there. I've listed UK, non-UK, R packages, and kind of other random data sources. You know, if you're in the middle of creating some research or writing a dissertation project and you're not quite sure where to obtain this data from, then here's a pretty good list for you. I've used the census data, I've used the UK police data, and what else have I used? I've obviously used shapefile data as well. The R packages, R itself does have packages that include APIs that allow you to connect straight to the UK police data, which is also really efficient. And the Crime R package has a lot of packages from America. I believe it's America. Yeah. But yeah, here's just a list of some crime data sources for those who are interested. So yeah, before kind of rounding up, I just wanted to talk about some the main challenges of mapping crime data. And this brings us on to what we know as geomasking and geoprivacy. Police police recorded crime provides point information through the use of GIS, like we've discussed. But the accuracy of this spatial data is obscured by geomasking techniques that basically serve to protect the location privacy of the victims. And what I mean is that even though we might have the point location of where a burglary might have happened, this location is actually jittered in that it kind of shakes a few grid cells, in that the exact location of this crime um, is never truth. It's never truly accurate. And this is because they have to protect the location privacy of our victims. You know, imagine if we all had access to where exactly all types of crime have happened across the UK. You can start to question why there would be limitations and you know, problems in ethics if we were to do this. So, like, yeah, what we think might have happened outside a school might not have actually happened right there. It might have happened the street up or around the corner. Um, Obviously, police recorded crime, again, unknown, are a known contribution to the grey figure. And this is where they basically underestimate the actual number of crimes recorded and not just reported, which reduces the accuracy of statistical models due to the missing data. Now, this isn't something that can be overcome in mapping techniques, unfortunately, but again, this is something that definitely has to be considered when conducting research. And there are some conceptual issues when working with police recorded crime data. For example, the definitions of some of these crime types are a little bit misleading in that the police recorded crime tends to combine two very, very distinct categories into one. So they tend to combine violent offences with sexual offences and view this as one crime type. So when you start to analyse this type of crime, you really have to think about the implications because we're providing a very holistic view of, you know, these crime trends rather than being able to look at the detailed differences between the two. And then we can think about impacts of seasonality. For example, how has COVID-19 affected the police recorded crime statistics, you know? Over the pandemic, researchers identified a reduction in some criminal activity as a result of lockdown rules. So what we saw was a reduction in burglary as more people have been forced to work from home, and there is this, you know, reduced opportunity to commit these crimes. So it's not entirely accurate to now hold year-to-year comparisons over the pandemic. We can't say that, you know, burglary was far less in 2019 than it was in 2020 without considering the effects of the pandemic. So yeah, just any other thoughts? Can you guys think of any more challenges that might come with mapping crime data specifically? Um, this is our last slide, and then I'm going to ask Emma to end the live stream in a minute. But yeah, if you can think of any more challenges that come with mapping crime data specifically, feel free to drop this in the chat. Sorry, drop this in the Mentimeter. And yeah, we'll have a little discussion if there's any more. We have a question here, so I think I'll call it quits on this slide. But we have a question that says, is it possible to map geo markers with non-geo data? Yes, this is possible, but this kind of depends on how you define a non-geo marker. So you could use, I guess, categorical or business data if that's what you mean. And then if you have the customer segments, you can overlay this information on a map without using the precise geographic information. So this would be postal codes, for example, or city names or market zones. But that is dependent on if you establish this as, you know, non-geo data. You can also map using hexagonal or grid-based mapping. So there's tools like the H3, which is the hexagonal grid system, which allows mapping data with direct geo coordinates. And there's also things like network-based market mapping. Let me just, yeah. Considering the time, I'm gonna just leave you here with my email and my Twitter. So if you do have any questions that you'd like to ask me personally, please feel free to email me or at me at Twitter, and I'll do my best to get a response back to you. Thank you all.